Welcome back, young students of chemistry. This is a short recording about equilibrium and what does it mean when a reaction reaches equilibrium. So here's the thing. To this point in honors chemistry, we have only studied reactions that go to completion, where you would have reactant A reacting with reactant B, yielding product, let's just say AB. And we have dealt with that. Those reactions have a forward arrow. We have used stoichiometric calculations to make relationships between reactants and products. We had a BDA chart, and after the reaction, there was at least one reactant that had 0 moles left over. And that's how we handled the stoichiometry of reactions that go to completion. So most reactions, however, do not go to completion, and they reach what is called a dynamic equilibrium. If someone has a dynamic personality, that means that they can adapt to a bunch of situations. They have a changing personality. And when we have a dynamic equilibrium, reactant A reacting with reactant B, forming product AB, what we end up with a situation is that after the reaction is over, there is some of everything. There are no zeros. No zeros. So you're going to have amounts in each of these categories here. The stoichiometry is still the same. We're still using coefficients for mole ratios. I call this chart something different. We call it an ICE chart. ICE stands for initial concentrations. C stands for the change in the concentration, and E stands for the equilibrium concentration. So the difference is here we only use moles. Here we can use moles or molarity. And you'll see when we start talking about the law of mass action why we can put molar concentrations. We could also use pressure here. I don't know that we'll get into that, but we can use pressure here. So here's your definition of equilibrium: a dynamic state in which the rate of reaction, the rate of the forward reaction, equals the rate of the reverse reaction. We indicate that both reactions can occur by the double arrow. And it makes sense. The word equilibrium suggests that something is equal. What students will often get confused and then get wrong is that they think that what is equal at equilibrium are the amounts of the substances, and that is just not true. What is equal are the rates, that the amount of time it's taking for the reactants to form products and the amount of time that it's taking for the products to break back up into the reactants. When equilibrium is established, there is still this process occurring, reactants bumping into each other and forming products, and products breaking up and forming reactants. It's just that we don't see it happen anymore. We don't see any more changes because they're happening at the same speed. And that's what we mean by dynamic. It's not static. It doesn't reach equilibrium and then the process is no longer occurring. It is constantly occurring. If we were to graph what equilibrium looks like, and we have on our graph moles on our y-axis and time on our x-axis, I'm going to make one block a second. So let's see, 2, 4, 6, 8, 10, 12 seconds, 14, 16, 18, 20 seconds. If we were to graph what it looks like for equilibrium to occur, I'm going to have equilibrium happen at 10 seconds here. how the moles change as time progresses is kind of what we're looking at here. So if we have moles of reactants, we would do moles of reactants and products. So starting here at 0, I want you to think about this. What do we have 0 of when the reaction occurs? And that is going to be products. So what happens as the reaction goes is that the products start at 0 and then they go up and up, and then they reach a point where they are no longer changing. And it is that point where the products have reached their equilibrium concentration. Now reactants, I really don't care how many moles you would use, but you would have reactants starting somewhere above 0, and as the reaction proceeds, the amount of the reactants goes down, and then at some point they would no longer change. That would be where equilibrium occurs. So what we have here is the point where equilibrium occurs in this region of the graph, between 10 and 18 seconds. We can see that the moles of reactants, if we call each of these lines a mole, 1 mole, 2 mole, 3 moles, 4 moles, that's unreasonable, by the way, 5 moles. But we can see that the moles of reactants are 4 moles, the moles of products are 6 moles. So the moles of reactants and products are not equal. It's just that they're no longer changing. And at this point also, we can see that at equilibrium, we have more products than we have reactants, right? The products moles were 6. The reactant moles were 4. So the product concentration at equilibrium is greater than the reactant concentration. So if we were going to write that in a chemical equation, we would say, okay, the forward reaction is the favored reaction. So reactants yielding products, we would write a long arrow in the forward direction and a shorter arrow in the reverse direction. That's one way to indicate that there'll be more products at equilibrium than there are reactants. Another way is with this value called the equilibrium constant. The equilibrium constant is abbreviated with a K, and we're going to talk about how we calculate that in a minute. But K, if K is greater than 1, that tells us that at equilibrium there's going to be more products than there are reactants. Let's look at a situation where that is not more products equal to reactants. Think about your graph and how it's going to change and how it's not going to change. So we have moles here on the y-axis, time on the x-axis. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I think I had equilibrium reached at 10 seconds. So you should think about this. If we're going to graph moles of reactants and products, does that change? And the answer to that question is no. We always start out with 0 products. Do the products still increase as the reaction occurs? Why, yes, they do. We always start with some reactants. Do the reactants still decrease when the reaction is occurring? And they still decrease. So the only thing that's different is that we have to have more moles of reactants at equilibrium than we have products. So if we think about how this graph is going to look different, this is still going to go down. These are still going to go up. But what's different is that the reactant moles will stay above the product moles. students will say, oh, well, the graphs don't cross. And that's true. Remember that point where where the two concentrations intersect each other doesn't really mean anything in terms of equilibrium. So here we have the equilibrium condition. If we were to draw this representation using reactants forming products, we would say that the reverse reaction is favored. So the forward reaction would have a smaller arrow than the reverse reaction. And then the value for the equilibrium constant, K, is going to be less than 1. And those are the ways we can indicate that the reaction is favoring reactants at equilibrium and not products. So there's a quick little introduction to equilibrium. In the next segment, we're going to talk about how to use the law of mass action to write equilibrium constant expressions, and then how to use that equilibrium constant expression to make calculations and figure out how much of what do we have at equilibrium.